Welcome to another exercise in the workbook statistics. This time with an exercise focusing on t-test for the coefficients of the regression line and the f-test. Well, let's have a look at our exercise. Here we have 5 randomly selected students are questioned about their preparation time for exams. The following table summarizes the time spent in preparation in hours and the points reached in the respective exam. So here, for 5 students, the points and the time. We can furthermore assume that the preparation time is the independent variable and the points reached is actually the dependent variable. With this in mind, our first task would be calculate the coefficient of determination, r squared, and assuming that the regression line is as follows. Second, conduct a suitable test with a margin of error of 5% to check whether the relation described by the regression is significant. Well, let's start directly with the first part with the calculation of the r squared. For this, we actually have two possibilities. We could just calculate, since we only have one x, one independent variable, we could just calculate Pearson's correlation coefficient and square this. However, in this case, we're going to use the standard approach for the coefficient of determination. And for this, I'm going to just copy the table and add one additional column with the averages. I'm going to do this for y and for x. And I'm going to add one row where I'm squaring all the y values, also calculating the average. And I'm going to add one additional row where I have these squared y hat values. What's the y hat? The y hat results from inserting the x values in the regression line. So here I'm going to take the 10, multiply this with the 1.1 something plus 69 something. Then if I get this result, I'm going to square the final one, giving me this in the end. Again, I'm going to square these results. If I want to know whether anything up or everything up to this step is at least supposedly relatively well done, I could compare these two values, because the y hat squared always needs to be smaller than the y squared. Why this is so, we're going to see in a moment. Once we have these values, we can use then the standard formula for the r squared, which is just the average of y hat squared. So it's here the 6,768 minus the average of y squared, so 82 squared, and all of this divided by the average of y squared. That's the 6,845 something. Again, minus the average of y squared, the 82 squared. If I calculate this, I will get 0.3679. Well, that's the r squared. That's a value always between 0 and 1, because this is the percentage of the variance of y which this model can explain. So here, our model can explain roughly 36.8% of the variance of y. Well, since the variance and the r squared thereof is always between 0 and 1, and if we look closely, if this value, so the y hat squared, would be on average larger than the y squared, the part in the upper area of this fraction would actually be larger than the one below here. So the denominator would be larger than the denominator, and this would result in an r squared of larger than 1. We said r squared is always smaller than 1, so this could not be the case. Thereby, the y hat squared always needs to be smaller than the y squared, or the average thereof. Well, this much for controlling our own results. We have our r squared, and now we want to conduct an f-test to test whether this is actually large enough so that we can say our model explains a significant share of the variance. Well, for the f-test, we're going to first calculate the test statistic, which is relatively straightforward. It's just r squared, which we have from part A, divided by k, which is the number of independent variables. Here we only have one x, so k is 1. And we're going to divide this fraction by another fraction, which is 1 minus r squared. And then divide this again by n minus k minus 1, n being the number of observations. So here we have 5 minus 1, giving us 3. So dividing this fraction by that fraction yields a test statistic of 1.7461. So that's the first part for the test. The second part is the determining of the reference statistic. This is something we get from the table on the F distribution. And here we have to look up the value f, k, n minus k minus 1, and 1 minus alpha. K, we know it's 1. N minus k minus 1, we know it's 3. And 1 minus alpha, alpha is the margin of error. We know from the exercise text, here the margin of error should be 1%. So we have 1 minus 0.01, so 0.99. This value we look up in the table for the F distribution, giving us as a reference statistic 34.116. So that's more or less all the stuff we need, because then we can compare test and reference statistic. Here we see that the test statistic is definitely smaller than the reference statistic. This tells us we cannot reject H0. In other words, the model does not contain significant explanatory power. So that's our insight here. We have a model. We can explain a bit more than 30-something%, but this is not enough so that we can say that the model has significant explanatory power. That's mainly due to the fact that we only have 5 observations, which is way too less for a decent linear regression. And well, that's about it on this exercise. I hope you enjoyed it. I say goodbye and see you next time.